Good morning, everyone. My name is John Borrow, and today I'll be presenting to you about my research project, quantum sensing using NV centers in nanodiamonds. NV centers in nanodiamonds are created when we use an electron beam and shine it onto a diamond crystal, thereby dislodging a carbon atom and replacing it with a nitrogen atom, creating an NV center, which is a solid-state spin defect that has a lone pair of electrons. So as we can see in our figure, we have two types of NV centers, the NV0 center and the NV minus center. In our research project, we will mainly focus on the NV minus center. We use two main techniques to study the structural, vibrational, and optical properties of the NV center: Raman spectroscopy and confocal microscopy. Raman spectroscopy provides an insight on the vibrational and electronic modes of the defect, which help us verify the NV centers by probing the Raman shift in energy. So as you can see, we focus on the red dot position, and this corresponds to the 3200 Raman shift position. When we use peak position to study the NV centers, we can see two NV centers on our left, and this also corresponds to 3200 peak position. The peak at the 1400 Raman shift position can be explained by the silicon substrate, which we placed our sample on, and is not really required when we are studying the NV centers. Confocal microscopy is another technique that we can use to study the properties of the NV centers. We typically use a green laser, since NV centers typically absorb light in the green part of the spectrum, and this wavelength is resonant with the electronic transitions of the NV centers, which simply means it provides the photons with enough energy equal to the energy gap so as it can be excited from a ground state to an excited state, which we will later see. Green lasers also reduce photobleaching, which is the irreversible loss in fluorescence, which is key in long-time imaging experiments that helps maintain longer coherence time. Confocal microscopy also has high spatial resolution imaging and helps us to individually study NV centers at a particular location. It also helps us do spectral analysis to identify different types of NV centers, which, as noted earlier, can be the NV0 center or the NV minus center. The microscope works on the principles that it rejects out of focus light, therefore allows for higher quality imaging of fluorescence. We can also do an optical readout to study the quantum state of the electron spin, which is key in aspects such as quantum computing. So the basic principles of the NV center is that the NV center has an S equals 1 electron spin, which has three possible spin states, m equals 0 and the m equals plus or minus 1 state. So as you can see in our figure, we optically pump or excite from an ms equals 0 state and to the ms equals plus or minus 1 state using the green laser. We can also see a subsequent decay occur where there's an emission of a red photon that can be detected using a photon detector. Therefore, there's spin preservation in both radiative and non-radiative decay. However, the NV center is more likely to undergo the metastable state, which is the non-radiative decay path from ms equals plus or minus 1 state to ms equals 0 state, and we can determine the relaxation time, which affects the coherence time we talked before, which is how long a qubit can maintain a superposition of state. Since the strength of photoluminescence depends on the spin state, the ms equals 0 is regarded as the bright state, and the ms equals plus or minus 1 state is regarded as the dark state. This can be read out graphically on a computer, and it tells us the electron spin state. We can also use microwave pulses to create a qubit in the NV center, and with this we manipulate the electron spin state, from up, which is a +1 state, or down, which is a -1 state. Manipulation of the electron spin state can happen through different operations, such as spin flip, which is when we change the direction of the electron spin. Therefore, we change its spin state from either +1 to -1 state. We can also create a superposition of state, and this helps us create a superposition of different spin states, which is key in quantum computing. The optical readout is done using a photodetector, which, as I mentioned earlier, can be done graphically on a computer. Relaxometry experiments are key in measuring the magnetic field, and this is done when the NV center senses the magnetic field of a particular sample that's brought close to its environment, which in this case is a gadolinium sample. Therefore, we can know quantitatively the behavior of the NV center under the external magnetic field that's applied on it. The change in energy level, which was described before due to the presence of magnetic field, is the basis for measuring the strength of the magnetic field. This is measured using electron spin resonance, and in this case we can measure the power spectrum of the gadolinium sample by determining its relaxation time. In this case, when the NV center does not have a gadolinium sample brought close to its environment, it has a higher relaxation time. But when the gadolinium sample is brought close to its environment, the relaxation time reduces, meaning we're able to determine the power spectrum of this particular sample, which is useful in engineering applications such as spintronics. Thank you and have a good day.